Hello, and welcome to Sleepy Engineering. In this video, we will explore the complete history, science, and application of one of the most unusual and fascinating practices in modern atmospheric engineering: cloud seeding. This narration is intentionally slow, detailed, and repetitive. It is designed to help you relax, focus, or fall asleep. There will be no sudden sounds, no music, and no emotional tone, only the steady voice of information. Now, please sit back, close your eyes if you like, and let the story of cloud seeding begin. Cloud seeding is a scientific practice that aims to modify weather patterns by encouraging clouds to release precipitation in the form of rain or snow, and it is often described as one of the most direct attempts at weather engineering, because it seeks to influence natural atmospheric processes in a controlled way. The idea is to take advantage of the fact that clouds contain water vapor and tiny droplets that sometimes remain suspended in the air without forming substantial rainfall. By introducing specific particles into these clouds, scientists attempt to provide nuclei around which moisture can condense and eventually fall to the ground as precipitation. The purpose of cloud seeding is multifaceted and has been explored in different parts of the world for more than 70 years. It has been promoted as a potential solution to drought relief, as a method to increase water supplies in agricultural regions, as a way to enhance snowpack in mountain ranges for hydropower and irrigation, and even as a tool to reduce the size and impact of damaging hailstorms. To understand why people turn to cloud seeding, one must first consider the challenges that societies face when it comes to water resources. In many regions, rainfall is irregular, and droughts can cause severe consequences for food production, drinking water, availability, and economic stability. By offering a technique that might increase the probability of rainfall, cloud seeding has been viewed by governments and industries as a possible supplement to natural water cycles rather than a replacement for them. The process does not create clouds out of nothing, and it does not generate water on its own. Instead, it attempts to maximize the efficiency of existing clouds by tipping the balance in favor of precipitation. Scientists generally use compounds such as silver iodide or sodium chloride because their crystalline structures are similar to natural ice and can trigger condensation or freezing processes within cloud droplets. When these particles are dispersed into the atmosphere, they serve as artificial ice nuclei, allowing supercooled water droplets to freeze and merge until they are heavy enough to fall to the ground as snow or rain. The purpose of such activity extends beyond simply making it rain. Farmers may rely on additional moisture during critical growing seasons. Municipal water managers may use seeding programs to replenish reservoirs in times of shortage. Ski resorts and hydroelectric power companies may invest in snowpack enhancement to secure winter tourism and stable energy supplies. Insurance companies and local governments may support hail suppression projects to reduce the economic damage from severe storms. In all these examples, the purpose is tied to human needs and the desire to mitigate the uncertainty of weather. The introduction of cloud seeding also reflects a broader human ambition to control, or at least influence, natural forces. Throughout history, people have dreamed of commanding the skies, whether through rituals, prayers, or mechanical inventions. Cloud seeding represents a scientific approach to this age-old wish. It takes the unpredictable realm of clouds and tries to apply engineering principles to guide their behavior, even if only slightly. While cloud seeding remains controversial in terms of effectiveness and ethics, its purpose has always been clear. It is not meant to replace the atmosphere or create new weather out of thin air, but to help societies cope with shortages and to provide a measure of resilience against climate variability. In this way, The introduction of cloud seeding stands as both a technical practice and a symbol of the ongoing human effort to adapt the natural world to human needs and aspirations. The story of weather modification begins long before the scientific era of cloud seeding, because humans have always been fascinated by the idea of influencing the sky and attempting to make rain fall when it was needed. Ancient cultures performed rituals, dances, and sacrifices in hopes of persuading the heavens to release water for crops and survival. These early efforts were rooted in mythology and spiritual belief, but they demonstrate how deeply connected human life has always been to rainfall and weather cycles. The transition from ritual to science began in the 19th and early 20th centuries, when researchers started to explore atmospheric processes with instruments and theories rather than prayer. One of the first notable ideas came from James Espy, an American meteorologist in the mid-1800s, who believed that large fires could stimulate convection and ultimately lead to rainfall, although his proposals were never fully tested at the time they planted the seeds for the concept of artificial rainmaking. Experiments in the late 19th century in the United States and parts of Europe involved the use of explosives, cannons, and balloons filled with chemicals to disturb clouds or release particles into the air. These attempts were largely crude and inconsistent, but they reveal the growing desire to use technology as a means of controlling nature. In the early 20th century, weather modification was sometimes tied to military or political ambitions, as well as agricultural needs. During periods of drought or food shortage, inventors claimed that they could induce rainfall through various contraptions. Some entrepreneurs toured towns with machines, promising to bring rain in exchange for payment. Yet most of these claims lacked scientific rigor and often ended in disappointment. Despite the questionable results, the notion of purposeful weather alteration persisted and gained more attention during World War II, when atmospheric science advanced rapidly. In the 1940s, researchers at General Electric in the United States began to investigate the role of ice nuclei in cloud formation. Vincent Schaefer discovered that dry ice could trigger the freezing of supercooled water droplets in laboratory clouds, while Bernard Vonnegut identified silver iodide as another effective agent. These breakthroughs represented a turning point because they were based on observable physical principles rather than speculation or superstition. The experiments soon moved from the laboratory to the sky. Aircraft were used to disperse dry ice and silver iodide into clouds over various locations in the United States, with some reports of increased snowfall or rainfall. Although the results were difficult to measure with certainty, the publicity surrounding these efforts marked the true beginning of modern cloud seeding. For the first time, there was a method grounded in atmospheric science rather than faith or conjecture. Governments and institutions took notice, and by the late 1940s and early 1950s, several organized programs had begun to explore cloud seeding as a tool for water management and weather control. The early history of weather modification therefore reflects a gradual shift from human imagination and ritual to experimental science. It highlights the persistence of an idea across centuries and the eventual development of practical techniques that could be tested, measured, and refined. These early experiments laid the foundation for decades of research that would follow, and they continue to influence the debates over cloud seeding today, because the origins of the practice reveal both the promise of scientific discovery and the cautionary tales of unfulfilled expectations. To understand the concept of cloud seeding, it is first necessary to understand how clouds themselves form and how precipitation naturally develops within the atmosphere. Clouds are essentially collections of tiny water droplets or ice crystals that become visible when moist air rises and cools. As air ascends into higher altitudes, the temperature drops and the water vapor it contains begins to condense around microscopic particles known as cloud condensation nuclei. These nuclei can be dust, pollen, sea salt, or other small particles suspended in the air. Without these nuclei, the water vapor would have difficulty condensing into droplets because it requires a surface to attach to. Once condensation begins, countless droplets cluster together and form the white or grey masses we see in the sky. The size and type of a cloud depend on the amount of moisture present, the altitude of formation, and the stability of the surrounding air. Precipitation, such as rain or snow, occurs when these droplets or crystals grow large enough to overcome the resistance of the air and fall to the ground. The growth of cloud particles happens primarily through two natural processes. The first is collision and coalescence, which occurs in warm clouds, where larger droplets fall faster than smaller ones and collide with them, gradually merging into even larger drops. Eventually, these drops become heavy enough to fall as rain. The second is the Bergeron-Feindeisen process, which takes place in cold clouds containing both supercooled water droplets and ice crystals. Because ice has a lower vapor pressure than liquid water, water vapor tends to deposit onto ice crystals while the liquid droplets evaporate. This imbalance causes the ice crystals to grow rapidly until they are heavy enough to fall as snow or melt into rain on their way down. These basic principles are central to cloud seeding because the practice attempts to encourage and accelerate processes that already occur in nature. By introducing additional nuclei such as silver iodide into a cloud, scientists hope to create more opportunities for water vapor to condense or freeze, thereby tipping the balance toward precipitation. However, not all clouds are suitable for seeding. If a cloud does not contain sufficient moisture, then adding nuclei will not result in rainfall. The presence of the right conditions is essential, including adequate humidity, appropriate temperatures, and atmospheric stability. Cloud seeding cannot make rain appear out of thin air. It can only increase the efficiency of existing clouds that already contain water, vapor, ready to be released. Another important principle in cloud physics is the idea of supersaturation, which occurs when the air contains more water vapor than it can normally hold at a given temperature. This state makes condensation more likely once a particle is introduced. Cloud seeding seeks to take advantage of this state by providing particles that trigger condensation or freezing before the vapor dissipates. These principles of cloud formation highlight the delicate balance within the atmosphere, where small changes in temperature, humidity, or particle availability can have significant effects on weather outcomes. By understanding these processes, scientists were able to imagine ways to influence them directly, leading to the modern practice of cloud seeding, which builds upon natural mechanisms rather than inventing new ones. The study of how clouds form and release precipitation remains essential to the evaluation of cloud seeding, because the practice depends entirely on enhancing the natural pathways that govern rainfall and snowfall. The science behind cloud seeding is grounded in the natural physics of clouds and precipitation, and it relies on the idea that under certain conditions, the addition of artificial particles can enhance the processes that cause rainfall or snowfall to occur. In essence, cloud seeding is not about creating water where none exists, but about making existing clouds more efficient at releasing the water vapor they already hold. Clouds are composed of tiny droplets of liquid water, or ice crystals, that form when moist air rises and cools. As explained earlier, condensation nuclei are the surfaces upon which water vapor condenses, and these nuclei can be natural particles such as dust or sea salt. Cloud seeding introduces artificial nuclei into clouds with the intention of encouraging more condensation or freezing to take place, thereby producing precipitation that might not otherwise occur. The most common agents used in cloud seeding are silver iodide, sodium chloride, and sometimes dry ice. Silver iodide is especially effective because its crystalline structure is very similar to that of ice. And when it is released into cold clouds containing supercooled water droplets, it acts as a template that encourages those droplets to freeze. Once freezing begins, ice crystals grow rapidly by attracting water vapor from surrounding droplets through the Bergeron-Findeisen process, which leads to the formation of larger ice particles that eventually fall as snow or melt into rain on their way down. Dry ice works differently because it causes rapid cooling when released into the cloud. This sudden drop in temperature can also trigger freezing in supercooled droplets. Sodium chloride is more commonly used in warmer clouds because it promotes condensation and coalescence of water droplets. These scientific principles allow cloud seeding to be adapted to different types of clouds and climates. Aircraft are often used to disperse these particles directly into or above clouds. Pilots release flares containing silver iodide or scatter powdered dry ice into specific regions of the cloud, depending on the atmospheric conditions. In some cases, rockets or artillery shells are used to deliver seeding agents into storm systems. And in other scenarios, ground-based generators burn solutions of silver iodide and release the particles into the air, where wind carries them upward into the target clouds. Regardless of the delivery method, the objective is always to place the particles where they can interact with cloud droplets most effectively. Once inside the cloud, the introduced particles alter the microphysical structure by providing additional surfaces for condensation or freezing. The theory is that by increasing the number of ice crystals or droplets, the cloud is pushed toward precipitation sooner or more intensely than it would have without intervention. It is important to emphasize, however, that cloud seeding cannot force a dry sky to produce rain. There must already be a cloud with enough water vapor to respond to the seeding process. Furthermore, the effectiveness depends on complex atmospheric variables, such as temperature, vertical air currents, and humidity, which makes results highly variable from one attempt to another. Despite these uncertainties, the scientific basis remains straightforward because it simply extends the natural pathways of precipitation with artificial assistance. The science behind cloud seeding illustrates a delicate interaction between human engineering and natural processes. It is not a method of controlling the weather completely, but a technique designed to nudge the atmosphere in a particular direction by amplifying the conditions that already exist. Understanding this science helps explain why cloud seeding continues to be both promising and controversial, because it demonstrates clear physical mechanisms, but depends heavily on the unpredictable behavior of clouds themselves. The choice of seeding agent is one of the most important factors in the practice of cloud seeding, because different particles interact with clouds in different ways and are suited to different atmospheric conditions. The most widely known and commonly used seeding agent is silver iodide, which has been employed since the 1940s due to its structural similarity to natural ice. Silver iodide forms a crystalline lattice that closely resembles the molecular arrangement of ice, and this property allows it to serve as an effective ice nucleus when introduced into clouds containing supercooled water droplets. Once these droplets encounter silver iodide particles, they are encouraged to freeze and grow into larger ice crystals, which can then fall as snow or melt into rain, depending on the temperature of the surrounding air. Silver iodide has remained the dominant agent because it is chemically stable, disperses well in the atmosphere, and requires only very small quantities to be effective. However, it is not the only substance used in cloud seeding. Another important agent is dry ice, which is the solid form of carbon dioxide. Dry ice works by rapidly cooling the air around it when it sublimates from a solid to a gas at very low temperatures. This intense cooling effect can cause supercooled droplets in the cloud to freeze without the need for structural similarity to ice crystals. Dry ice is generally deployed from aircraft because it must be released directly into the cold parts of a cloud to be effective. Unlike silver iodide, which relies on chemical properties, dry ice relies on physical cooling and therefore works best in specific cloud conditions. A third category of seeding agents involves simple salts, such as sodium chloride or potassium chloride, which are especially effective in warmer clouds, where the objective is to encourage condensation rather than freezing. These salts attract water vapor due to their hygroscopic properties, meaning they readily absorb moisture from the air. When dispersed into a cloud, the salt particles can grow rapidly by condensation and can promote the coalescence of small droplets into larger ones. Eventually, these larger droplets may become heavy enough to fall as raindrops. This method is often considered for tropical regions where clouds are warmer and do not contain significant amounts of supercooled water. In addition to these main agents, research has explored other materials such as calcium, chloride, urea, or even biodegradable organic particles. Each material has its own advantages and limitations. For instance, while salts are inexpensive and readily available, they require clouds with high humidity to function effectively and may be less efficient in dry conditions. Silver iodide, while effective at small concentrations, has raised concerns about potential environmental accumulation. Though studies generally suggest the quantities used are too low to cause significant harm, dry ice is effective, but logistically more difficult to transport and apply because of the need for cold storage and rapid deployment. Cloud seeding agents can also be engineered into flares, cartridges, or pyrotechnics that are burned or released from aircraft or ground-based generators. The choice of dispersal method is closely tied to the type of agent being used and the desired outcome. Whether the goal is snowfall, enhancement, rainfall, stimulation, or hail suppression, the agent must match the physics of the target cloud. The properties of these agents highlight the delicate balance required for successful seeding, because even though the concept seems simple in practice, it requires precise matching of material, cloud type, and environmental condition. This explains why cloud seeding projects are often carefully designed with meteorological monitoring and scientific oversight. The agents themselves embody the principle of working with nature rather than against it by taking advantage of natural chemical or physical processes already present in the atmosphere and amplifying them toward a desired outcome. The effectiveness of cloud seeding does not depend only on the choice of seeding agent, but also on how that agent is delivered into the atmosphere, because the method of dispersal determines whether the particles will actually reach the correct part of the cloud and interact with the water droplets or ice crystals in the intended way. One of the most common and versatile methods is the use of aircraft, which can fly directly into or above target clouds and release seeding agents in a controlled manner. Aircraft often carry flares or pyrotechnic devices containing silver iodide that are ignited under the wing, allowing the particles to drift into the cloud as the plane passes through. In other cases, aircraft drop powdered dry ice pellets directly into the supercooled regions of a cloud, where the intense cooling effect can trigger ice formation. Pilots and meteorologists work closely together in these operations because timing altitude and the specific part of the cloud that is targeted are all critical to success. Aircraft-based, seeding is flexible and precise, but it is also expensive and requires trained crews and specialized equipment. A second method that has been used, especially in large-scale programs, involves rockets or artillery shells filled with seeding agents. These devices can be launched from the ground into the base or sides of a cloud, where they explode and disperse the material over a wide area. This approach has been popular in China and other countries that conduct weather modification on a national scale because it allows for rapid deployment over large regions without the need for fleets of aircraft. Rockets are less precise than planes, but they can reach storm systems that may be too dangerous or inaccessible for piloted flights. They are also effective for hail suppression programs, where rapid and widespread dispersal of seeding particles is necessary to influence the development of hailstones before they become damaging. A third method that has gained attention for its relative simplicity and cost-effectiveness is the use of ground-based generators. These generators typically burn a solution of silver iodide and acetone, creating microscopic particles that rise into the atmosphere with the natural air currents and wind. The idea is that prevailing winds will carry the particles into the target clouds above, especially when the seeding site is located in mountainous terrain, where orographic lifting naturally pushes moist air upward. Ground generators are often used in programs that aim to increase snowpack in mountainous regions to support water supplies and hydroelectric power. Because they do not require pilots or rockets, they can operate continuously during suitable weather conditions and are less costly to maintain. However, their success depends heavily on wind direction and atmospheric stability, which makes them less predictable than aircraft delivery. Each of these methods of delivery has advantages and disadvantages. Aircraft provide precision and flexibility, but at high cost and with safety risks. Rockets offer speed and wide coverage, but with less control and potential concerns about debris. Ground generators are inexpensive and practical in certain environments, but limited by weather and geography. In many cloud seeding programs, a combination of these methods is employed to maximize effectiveness depending on local conditions and objectives. The choice of delivery system must always be matched carefully to the type of cloud the seeding agent being used and the overall goal of the project, whether it is rainfall enhancement, snowpack accumulation, or hail suppression. The methods of delivery represent the engineering side of cloud seeding because they involve the practical logistics of moving material from the ground into the sky in the right way at the right time. They illustrate how cloud seeding is not just about scientific theory, but also about operational strategy and the management of complex atmospheric interventions. The United States has been one of the earliest and most active countries in experimenting with and applying cloud seeding, and a number of case studies illustrate both the potential and the challenges of this technology. The story begins in the late 1940s, when researchers at General Electric in New York, including Vincent Schaefer and Bernard Vonnegut, conducted the first modern cloud seeding experiments using dry ice and silver iodide. These experiments demonstrated in a controlled way that supercooled water droplets could be forced to freeze and create snow or rain. And soon afterward, the technique was tested in the open atmosphere in locations such as Massachusetts and New Hampshire. The early success generated public interest, and soon several states began to experiment with cloud seeding programs, particularly in the western United States, where water scarcity has always been a pressing issue. One of the most notable long-running examples is the cloud seeding projects conducted in the Sierra Nevada mountains of California. These projects aim to increase the snowpack during winter, because the snowmelt is a crucial water source for agriculture. Cities and hydroelectric power generation studies conducted by organizations such as the Desert Research Institute and utilities like the Pacific Gas and Electric Company have suggested that cloud seeding in this region can produce measurable increases in snowfall, although the exact percentages are debated. Another significant case study comes from the state of Colorado, where cloud seeding has been used extensively in the Rocky Mountains to enhance snowpack for water supplies in the Colorado River Basin. Because this river provides water to multiple states, including Arizona, Nevada, and California, even small increases in snowpack can have major benefits for millions of people and for agricultural production throughout the Southwest. Colorado's cloud seeding programs often rely on ground-based generators located at high elevations, which release silver iodide particles into the prevailing winds that carry them into suitable storm systems. Further examples can be found in Texas, which has conducted cloud seeding for drought relief since the 1950s, in a state that frequently suffers from long dry periods. Water for farming, ranching, and urban use is often scarce, and cloud seeding has been explored as one method of increasing rainfall. The Texas Weather Modification Association has managed several regional projects involving both aircraft and ground generators, and while results vary with weather conditions, some studies have reported modest increases in rainfall during seeded storms. In North Dakota, cloud seeding has been applied not only for rainfall enhancement, but also for hail suppression. Farmers in this agricultural region face serious losses when large hail damages crops, and cloud seeding has been promoted as a means of reducing hailstone size by encouraging the formation of many smaller ice particles rather than fewer large destructive ones. Although it remains difficult to prove statistically, the program has been maintained for decades, reflecting the strong local support it enjoys. Beyond these state-level initiatives, there have also been federal research projects, such as Project Storm Fury in the 1960s, which attempted to use cloud seeding to weaken hurricanes by altering their internal structure. Although the results were inconclusive and the project was eventually abandoned, it represents one of the most ambitious efforts to apply cloud seeding on a large and experimental scale. Together, these case studies from the United States show a wide variety of goals, ranging from drought relief and snowpack enhancement to hail suppression and even hurricane modification. They highlight the flexibility of cloud seeding, but also its uncertainties, because while some studies point to clear benefits, others stress that the evidence remains difficult to measure conclusively. Nevertheless, the long history of cloud seeding in the United States demonstrates the persistence of the idea and the willingness of states, industries, and communities to invest in the possibility of gaining even modest improvements in water security and weather resilience. China has become one of the most ambitious nations in the world when it comes to cloud seeding, with large-scale programs that dwarf many of those conducted in the United States or Europe. The Chinese government has invested heavily in weather modification since the 1950s, and today the country operates thousands of personnel and numerous aircraft dedicated to seeding operations. One of the most famous applications occurred during the 2008 Beijing Olympic Games, when officials used cloud seeding to reduce the likelihood of rainfall during opening ceremonies by attempting to trigger precipitation in clouds before they reach the city. China's program is not limited to single events, however, and extends across vast regions for the purposes of increasing rainfall in arid areas of the north. enhancing snowpack in the Tibetan Plateau and reducing hail damage in agricultural provinces. The sheer scale of the program demonstrates both the technological capacity and the political will to experiment with weather modification on a national level. In addition to China, many other countries have pursued their own cloud seeding initiatives. Russia has a long history of weather modification, dating back to Soviet times, when cloud seeding was used for military and civilian purposes. During state parades and celebrations such as May Day events, seeding agents were released into the atmosphere to disperse clouds and ensure clear skies. More recently, Russia has used cloud seeding to reduce hail damage in farming regions and to attempt rainfall enhancement in water scarce areas. The Middle East is another region where cloud seeding has gained attention due to persistent drought conditions. The United Arab Emirates, in particular, has sponsored extensive cloud seeding programs in collaboration with international research institutions. Aircraft equipped with salt flares are deployed to stimulate rainfall in convective clouds over the desert. The UAE has also invested in advanced monitoring systems and has hosted competitions encouraging scientists to develop new materials and techniques for weather modification. Their efforts reflect the urgent need for alternative water sources in arid environments and their willingness to explore experimental technologies. In Australia, cloud seeding has been employed primarily in Tasmania, where hydroelectric power is a key part of the energy supply. Since the 1960s, the Hydroelectric Commission has conducted seeding experiments over the mountainous regions of the island to increase rainfall and support dam reservoirs. Long-term studies have suggested that seeding operations in Tasmania have led to measurable increases in precipitation, providing valuable lessons for other regions with similar geography. India has also experimented with cloud seeding, particularly in the states of Maharashtra and Karnataka, where monsoon variability causes major challenges for agriculture. Aircraft-based operations have been used to enhance rainfall during deficient monsoon years, and while results are debated, the practice continues to attract government support. South Africa has tested cloud seeding for both rainfall enhancement and hail suppression, with projects conducted in the Highveld region, where hail frequently damages crops. In Europe, countries such as France, Spain, and Greece have carried out hail suppression programs for decades, particularly in wine-growing regions, where hail can destroy harvests in minutes. These projects rely largely on aircraft or ground generators that disperse silver iodide into storm systems. While smaller in scale than programs in China or the United States, they demonstrate the widespread appeal of cloud seeding across different climates and economic contexts. Taken together, these international examples show that cloud seeding is not confined to one nation or region, but has been pursued globally wherever water scarcity, agriculture, or weather hazards create pressures on human societies. Each country adapts the technology to its own needs and resources, whether for drought, relief, crop protection, energy, generation, or national events. The diversity of these efforts also highlights the varying levels of investment and belief in the technique, with some nations building vast operational systems, while others limit their efforts to local experiments. Regardless of differences, all of these projects contribute to the shared global story of cloud seeding as a tool of weather modification that reflects the universal human desire to manage the uncertainties of the atmosphere. When discussing cloud seeding, it is important to examine the environmental impacts and ecological considerations, because altering atmospheric processes raises questions about unintended consequences on ecosystems and human health. The first concern often raised is the use of silver iodide, which has been the most common seeding agent for decades. Silver iodide is a chemical compound that resembles ice in structure, making it effective in cloud nucleation, but some people worry about its accumulation in soil and water. Studies generally suggest that the amounts used in seeding operations are very small and well below toxic thresholds for plants and animals. Yet long-term and large-scale deployment continues to prompt debate about possible build-up over time. Environmental agencies and researchers have conducted monitoring programs in areas with active seeding, and so far have not found evidence of widespread ecological damage. But the perception of risk remains an important consideration. Another ecological question relates to the redistribution of rainfall. If precipitation is increased in one region through cloud seeding, some critics argue that it may deprive neighboring regions of their natural share of rainfall. The scientific consensus is that cloud seeding does not steal water from other areas, because the atmosphere contains more moisture than any single storm can release, and clouds often dissipate without producing precipitation. However, proving this in practice is challenging, because weather systems are dynamic and interconnected, which makes it difficult to isolate the precise effect of seeding on downwind regions. This uncertainty can lead to political or social tensions, particularly in areas where water rights are contested. Beyond chemical and distributional concerns, there is also the question of ecological balance. Precipitation patterns play a central role in shaping ecosystems, and altering the timing or amount of rainfall could potentially disrupt plant growth, wildlife habitats, and seasonal cycles. For example, if cloud seeding were to enhance rainfall during certain months, it could change the flowering patterns of plants or the migration habits of animals that rely on predictable weather cues. These effects are largely theoretical, but they underscore the complexity of interacting with atmospheric systems. On the other hand, some argue that cloud seeding can have positive environmental impacts by mitigating droughts that would otherwise devastate ecosystems and human communities. By increasing water availability for crops, forests, and rivers, seeding may help support biodiversity during periods of scarcity. Similarly, snowpack enhancement in mountain regions can stabilize water supplies for downstream habitats and fisheries, providing ecological benefits that counterbalance the risks. The energy and climate implications must also be considered. Cloud seeding often requires aircraft flights, which consume fuel and produce emissions, although the scale is relatively small compared to commercial aviation. There is also a broader climate consideration, because weather modification touches on ethical questions about human intervention in natural systems. While cloud seeding is far less disruptive than geoengineering proposals that aim to alter global climate, it still represents a step toward deliberate manipulation of the environment. And this raises concerns about governance, consent, and ecological stewardship. In recent years, some scientists have advocated for more rigorous environmental impact assessments before large-scale cloud seeding programs are implemented. They emphasize the importance of long-term monitoring of soil water and biota in seeded regions to ensure that no hidden effects accumulate over decades. The ecological debate over cloud seeding ultimately reflects the larger challenge of balancing human needs for water and agriculture with the responsibility to protect natural systems. While most evidence so far suggests that cloud seeding has minimal harmful impacts, the uncertainties demand caution and transparency. The practice sits at the intersection of engineering and ecology, reminding us that even modest attempts to influence the atmosphere must be evaluated not only for their effectiveness, but also for their harmony with the natural world. Cloud seeding is not only a scientific and engineering practice, but also a subject of ethical debate and public perception, because altering the weather touches on sensitive questions about human responsibility and authority over natural systems. One of the primary ethical questions is whether it is right to intervene in the atmosphere at all. Weather has always been viewed as a natural force beyond human control, and the idea of deliberately changing precipitation patterns challenges deeply held cultural and philosophical beliefs about the relationship between humanity and nature. Some critics argue that by attempting to modify weather, people may overstep their boundaries and create unforeseen consequences that harm ecosystems or communities. Another ethical concern involves fairness and equity, because the benefits of cloud seeding are not always shared equally. If one region invests in cloud seeding to increase rainfall, neighboring areas may worry that their share of precipitation will be reduced. Even though most scientists insist that cloud seeding does not rob other regions of rain, the perception of unfairness can fuel disputes, especially in places where water scarcity is already a source of conflict. This raises questions about who has the right to decide when and where cloud seeding should occur, and whether such decisions should be made locally, nationally, or even internationally. Public perception is also shaped by trust in the science itself. Many people remain skeptical about the effectiveness of cloud seeding because results are difficult to measure conclusively. When rainfall increases after a seeding operation, it is hard to prove whether the increase was caused by the intervention or by natural weather variability. This uncertainty creates space for doubt, and in some cases, suspicion. People who are affected by droughts or floods may question whether weather modification programs are helping or making conditions worse. There are also ethical issues tied to transparency and informed consent. In some regions, cloud seeding operations are conducted without the full knowledge of the local population, which can lead to feelings of exclusion or mistrust. Communities may want a say in whether their skies are seeded, especially if they fear potential environmental or health risks. Clear communication about the goals, methods, and limitations of cloud seeding is therefore essential to maintaining public confidence. Beyond these concerns, cloud seeding can evoke broader fears about weather control and manipulation. Popular culture has often portrayed weather modification as a form of technological hubris, or even a weapon. Historical examples, such as the reported use of cloud seeding during the Vietnam War to extend monsoon rains, reinforce worries about the potential for misuse in military or political contexts. These associations can make the public wary, even when cloud seeding is conducted purely for civilian purposes like agriculture or water supply. At the same time, there are also positive perceptions. Many farmers and water managers view cloud seeding as a valuable tool that can help reduce the impacts of drought, protect crops from hail, and stabilize water resources. For communities facing increasing climate variability, the promise of even a small improvement in precipitation can outweigh abstract ethical concerns. Public perception therefore varies widely, depending on local needs, historical experiences, and levels of trust in scientific and governmental institutions. The ethical questions surrounding cloud seeding ultimately highlight the tension between human ingenuity and the limits of natural systems. On one hand, the technology represents a rational attempt to adapt to water scarcity and extreme weather. On the other hand, it raises profound issues about consent, fairness, and responsibility. Addressing these concerns requires not only scientific research, but also ethical reflection and public dialogue, ensuring that the pursuit of weather modification is guided not just by technical feasibility, but also by social values and respect for the communities and ecosystems it may affect. Cloud seeding is often discussed not only in the context of local weather modification, but also in connection with the broader challenges of climate change, because both issues revolve around humanity's attempt to manage atmospheric processes in the face of growing environmental pressures. Climate change is altering precipitation patterns across the globe, with some regions experiencing more intense rainfall and flooding, while others face prolonged droughts and shrinking water supplies. Against this backdrop, cloud seeding has been proposed by some as a potential adaptation strategy, a way to supplement water resources or mitigate the impacts of extreme weather. The basic idea is that by enhancing precipitation in areas suffering from reduced rainfall, cloud seeding could help maintain agricultural production, replenish reservoirs, and support ecosystems that might otherwise be stressed by climate variability. Supporters argue that even small percentage increases in rainfall could have significant benefits in drought-prone areas, especially as climate change intensifies water scarcity. For instance, additional snowpack generated by cloud seeding in mountainous regions could provide a buffer against earlier spring melting and diminished summer flows that are linked to warming temperatures. By stabilizing water supplies, cloud seeding could reduce some of the risks associated with a changing climate. However, the relationship between cloud seeding and climate change is complicated because the practice is highly localized and limited in scope compared to the global forces driving climate systems. While seeding can potentially influence the microphysics of a particular cloud, it cannot counteract the large-scale warming caused by greenhouse gas emissions. This distinction is important because some fear that the promotion of cloud seeding as a climate adaptation tool may create false hope or distract from the urgent need to reduce carbon emissions. Another aspect of this relationship involves the comparison between cloud seeding and geoengineering. Geoengineering refers to large-scale interventions designed to counteract global warming, such as injecting particles into the stratosphere to reflect sunlight. Cloud seeding is much smaller in scale and aims to manipulate precipitation rather than temperature. But the two practices are often discussed together because they both represent intentional modifications of natural atmospheric processes. This association can contribute to ethical concerns, as critics worry that experimenting with weather on any scale may set a precedent for more radical interventions in the future. Climate change also adds uncertainty to cloud seeding itself, because shifting weather patterns may alter the types of clouds available for seeding, their frequency, and their response to seeding agents. For example, in some regions, warming temperatures may reduce the occurrence of supercooled clouds that are most responsive to silver iodide, making traditional methods less effective. In other regions, more intense convective storms may change the dynamics of rainfall in ways that complicate seeding strategies. Scientists stress that cloud seeding should be viewed as one of many possible tools in a broader adaptation portfolio rather than a standalone solution. From a social perspective, climate change intensifies debates about fairness and governance in cloud seeding, because water scarcity is becoming more politically sensitive. As nations struggle to secure resources, the use of weather modification technologies could create international tensions, especially in regions where rivers or weather systems cross borders. Questions about who gets to control rainfall and who bears the risks of unintended consequences are magnified in a world already strained by climate impacts. Despite these concerns, research into cloud seeding continues to attract interest as part of climate resilience planning. Pilot projects in arid and semi-arid regions emphasize the need to explore every possible option for sustaining water supplies, and cloud seeding offers a relatively low-cost and low-energy approach compared to massive infrastructure projects like desalination plants or new dams. Its role in the era of climate change is therefore best described as supplementary. It cannot reverse or stop warming, but it may help soften some of its local effects. The relationship between cloud seeding and climate change is ultimately a reflection of the broader human struggle to adapt to a rapidly shifting planet, demonstrating both the ingenuity of scientific intervention and the limits of technological fixes when confronting global environmental challenges. The effectiveness of cloud seeding has been a subject of debate since the earliest experiments, because measuring the true impact of seeding on precipitation is extremely difficult, and this uncertainty has led to both optimism and skepticism in scientific and public discussions. At the heart of the issue lies the complexity of weather systems, which are influenced by countless variables such as temperature, humidity, wind patterns, and atmospheric stability. When rainfall occurs after a cloud seeding operation, it is challenging to determine how much of that rain would have fallen naturally without human intervention. To address this challenge, scientists have developed statistical methods and randomized experiments where some clouds are seeded while others are left untouched in order to compare outcomes. Some studies have reported increases in precipitation ranging from 10 to 20% under favorable conditions, suggesting that cloud seeding can indeed enhance rainfall or snowfall when clouds contain sufficient moisture and are properly targeted. For example, projects in the Sierra Nevada in California and in the Rocky Mountains of Colorado have provided evidence that snowpack can be increased in seeded areas, supporting water supplies for downstream reservoirs and agriculture. Similarly, experiments in Israel conducted during the latter half of the 20th century suggested that cloud seeding led to measurable rainfall increases, although later evaluations questioned the consistency of those results. Other research has found more modest or even negligible effects, leading to the conclusion that cloud seeding is highly dependent on local conditions and may not work reliably in all environments. One of the main controversies arises from the difficulty of conducting perfectly controlled experiments in the atmosphere. Unlike laboratory science, weather modification cannot isolate variables completely, and even with sophisticated models and statistical designs, there is always some level of uncertainty. This means that while cloud seeding can be shown to have physical plausibility based on known microphysical processes, proving its consistent effectiveness in the real world remains elusive. Another point of controversy concerns hail suppression. Some programs claim that seeding can reduce the size of hailstones and thereby minimize agricultural damage, but critics argue that evidence for this effect is weak and inconsistent. Farmers who support these programs often point to anecdotal improvements, while scientists caution that long-term statistical data is required before drawing firm conclusions. Internationally, effectiveness results have been similarly mixed. In China, officials report large increases in rainfall from cloud seeding operations, but independent verification is difficult, and some observers suggest that results may be overstated due to political or institutional incentives. In the United Arab Emirates, where cloud seeding has been pursued vigorously, some studies suggest promising increases in rainfall, yet questions remain about whether the observed effects are reproducible over time and across different atmospheric conditions. Another layer of controversy involves cost effectiveness. Even if cloud seeding produces modest increases in precipitation, the expense of aircraft, rockets, or generators must be weighed against the value of the additional water gained. In some cases, the benefits may outweigh the costs, especially when water scarcity is severe, but in other cases, the return on investment is less convincing. Environmentalists also raise concerns about long-term impacts, arguing that without clear evidence of effectiveness, it may not be wise to release chemicals like silver iodide into the environment, even if studies so far show minimal risk at the concentrations used. The debate over effectiveness also touches on public perception and trust in science. Supporters argue that cloud seeding represents a promising tool for adaptation to water scarcity and climate variability, while critics see it as an uncertain and potentially overhyped technology that diverts attention from more reliable water management strategies such as conservation, recycling, and infrastructure improvements. The controversy is unlikely to be resolved quickly because proving causality in complex atmospheric systems is inherently difficult. Nevertheless, research continues with the hope that improved monitoring, satellite data, and climate modeling will provide clearer answers in the future. In summary, cloud seeding's effectiveness remains both promising and controversial, supported by physical principles and some positive field results, but challenged by variability, measurement difficulties, and conflicting evidence, making it a subject where science, policy, and perception intersect in ongoing debate. While many people associate cloud seeding primarily with efforts to increase rainfall in drought-stricken regions, the technology has also been applied in other ways that go beyond simple rainfall stimulation. Two of the most important alternative applications are snowpack enhancement and hail suppression, both of which have been explored for decades in different parts of the world. Snowpack enhancement is particularly significant in mountainous regions, where snow accumulation during the winter months serves as a natural reservoir that gradually melts in spring and summer to supply rivers, lakes, and hydroelectric dams. In areas such as the Sierra Nevada in California, the Rocky Mountains in Colorado, and the Snowy Mountains in Australia, cloud seeding has been used to encourage additional snowfall in order to secure water resources for downstream agriculture, cities, and energy production. The principle is the same as rainfall seeding, but targeted toward colder clouds, where silver iodide particles can induce freezing in supercooled water droplets to form snow crystals. By enhancing snowpack, water managers can reduce the risk of shortages during dry seasons and provide more stable supplies for both human and ecological needs. This application is often considered one of the most practical uses of cloud seeding because snowpack levels can be measured directly and correlated with long-term water storage outcomes, making the benefits easier to evaluate compared to rainfall projects where variability is higher. Another major application is hail suppression, which addresses a different kind of weather challenge. In many agricultural regions, hailstorms can cause devastating damage to crops, infrastructure, and property in just a few minutes. And reducing the size and intensity of hailstones has been a long-standing goal of weather modification programs. The theory behind hail suppression is that by seeding storm clouds with silver iodide or other agents, the number of ice nuclei inside the cloud is increased, leading to the formation of many smaller ice particles rather than fewer large hailstones. If successful, this process can result in precipitation falling as rain or as small, harmless pellets instead of large, destructive hailstones. Countries such as France, Greece, and South Africa have maintained hail suppression programs for decades, particularly in wine-growing and farming regions, where crop losses can be severe. In the United States, states like North Dakota have also supported hail suppression as part of broader weather modification efforts to protect agriculture. Evaluating the success of hail suppression programs has been challenging, as with rainfall enhancement, but many farmers and regional governments continue to support the practice based on both scientific studies and long-term experience. Beyond snowpack and hail, cloud seeding has occasionally been applied for event-specific purposes, such as clearing skies for public ceremonies or preventing rainfall during national holidays, though these uses are more symbolic and politically driven than practical. Still, they highlight the versatility of the technology and the wide range of goals that humans pursue when attempting to manage the atmosphere. The broader point is that cloud seeding is not a one-dimensional tool, but a flexible set of techniques that can be adapted to different weather-related challenges depending on local needs. Whether the goal is to store more water in snowpacks, to shield crops from hail, or to improve rainfall in dry regions, the underlying science of cloud microphysics provides the foundation for intervention. At the same time, these applications face the same uncertainties and controversies as rainfall enhancement. Because while the physics makes sense, the variability of weather makes results hard to prove conclusively. Nevertheless, the continued use of snowpack enhancement and hail suppression demonstrates that many communities see value in pursuing even modest improvements when the stakes are as high as food security, water supply, and economic stability. Cloud seeding in these forms remains a practical expression of humanity's long-standing effort to adapt natural forces to human needs and to find creative ways of reducing the risks posed by an unpredictable atmosphere. Because cloud seeding directly intervenes in natural atmospheric processes, it inevitably raises legal and political questions about regulation, responsibility, and oversight. From its earliest experiments in the mid-20th century, governments recognized that weather modification could not remain an unregulated activity, especially when multiple communities, or even multiple nations, might be affected by a single operation. In the United States, for example, weather modification has been subject to federal and state-level reporting requirements since the 1970s. The National Weather Modification Reporting Act requires that any person or organization conducting cloud seeding must notify the government and provide data about the activity. This ensures that programs are tracked, not only for scientific monitoring, but also to promote transparency and reduce the risk of disputes between regions. At the state level, many western states, such as Colorado, Texas, and Utah, have agencies that oversee cloud seeding projects, issue permits, and require environmental assessments. These frameworks are designed to provide accountability and to reassure the public that seeding operations are being conducted safely and responsibly. On the international stage, weather modification intersects with broader concerns about sovereignty and shared resources. Precipitation patterns do not respect political borders, and this creates potential conflicts when one country seeds clouds that drift into or originate from another nation's territory. To address such concerns, the international community has established legal agreements, the most prominent being the United Nations Convention on the Prohibition of Military or any other hostile use of environmental modification techniques adopted in 1977. Known as the MOD Convention, this treaty prohibits the use of weather modification for hostile purposes, such as warfare, but does not forbid peaceful applications like agricultural cloud seeding. Still, the convention reflects global recognition that weather modification is powerful enough to require legal boundaries. Beyond international treaties, cloud seeding has also raised political debates about governance and fairness within nations. Some communities argue that seeding in one region could deprive another of rainfall, even if scientific evidence suggests otherwise. These disputes highlight the importance of establishing clear rules for consultation and consent before programs are launched. In democratic societies, public hearings and environmental reviews are often part of the approval process for weather modification projects, ensuring that stakeholders can voice their concerns. In more centralized political systems, such as in China, cloud seeding programs are coordinated by national agencies and implemented at a scale that reflects state priorities rather than local choice. This difference shows how political systems shape the way weather modification is managed and perceived. Legal frameworks also extend to liability. If cloud seeding were alleged to cause flooding, hail damage, or other adverse outcomes, questions would arise about who is responsible and whether affected parties could seek compensation. Although proving causation is extremely difficult in meteorology, the possibility of lawsuits or disputes adds another layer of complexity to the legal environment. Some jurisdictions require cloud seeding operators to carry insurance or provide guarantees as part of their licensing conditions. Another political dimension involves international cooperation. In regions where water resources cross borders, such as river basins in Africa, Asia, and the Middle East, the use of cloud seeding could become a diplomatic issue. Joint management agreements may be necessary to ensure that seeding programs are coordinated and do not create unnecessary conflict. Finally, the legal and political frameworks surrounding weather modification are evolving in response to climate change. As droughts become more severe and water security more pressing, pressure is mounting on governments to explore cloud seeding more actively. This creates opportunities for new legislation, updated regulatory systems, and possibly new international treaties that clarify how and when weather modification should be used. The existence of these frameworks underscores that cloud seeding is not simply a technical matter, but a political and legal one, where questions of authority, fairness, and responsibility are just as important as the underlying science. The future of cloud seeding is shaped by both technological innovation and the increasing urgency of global water challenges, and many researchers and policymakers see it as an evolving field that could play a larger role in climate adaptation and resource management. Traditional methods using silver iodide, sodium chloride, or dry ice have been tested for decades, but new materials and techniques are being explored to improve efficiency and reduce environmental concerns. One area of development involves nanotechnology, where scientists are experimenting with nanoparticles designed to mimic the structure of ice more precisely or to act as more effective condensation nuclei in warmer clouds. These engineered particles may offer greater control over the microphysical processes inside clouds, while requiring smaller quantities of material, thereby reducing potential ecological risks. Another emerging technology is the integration of cloud seeding with advanced weather prediction models and satellite monitoring. In the past, seeding operations were often based on limited observational data, which made targeting less precise. Today, improvements in remote sensing and computer modeling allow meteorologists to identify which clouds are most suitable for seeding and to time operations more accurately. Drones are also being considered as delivery systems, offering a cheaper and safer alternative to piloted aircraft and rockets. Autonomous drones equipped with seeding flares could operate in difficult or dangerous weather conditions, increasing the flexibility of programs while lowering costs. Beyond delivery systems, researchers are also studying alternative chemicals that could replace silver iodide, which, although used in very small amounts, continues to raise environmental questions. Biodegradable organic compounds, salts tailored to specific humidity conditions, or even naturally occurring minerals are being tested as potential substitutes. Some experiments also explore the use of lasers to trigger condensation in the atmosphere by ionizing particles and creating pathways for water vapor to condense. While still experimental, such approaches highlight the creativity being applied to the future of weather modification. The role of cloud seeding in climate change adaptation will likely expand as water scarcity becomes more acute. Countries facing recurring droughts, such as those in the Middle East, Africa, and parts of Asia, are already investing in long-term programs. And as technology advances, the appeal of cloud seeding as a relatively low-cost and scalable tool is likely to grow. International cooperation may also become more important, with shared research and cross-border agreements helping to establish common standards and reduce the risk of conflict. However, the future of cloud seeding is not free from controversy. Critics warn that over-reliance on weather modification could distract from essential investments in conservation, water recycling, and sustainable infrastructure. There are also ethical concerns that advanced technologies could deepen inequalities if only wealthy nations or corporations can afford them. Furthermore, the unpredictability of weather systems means that cloud seeding will never provide absolute certainty, and inflated expectations could lead to disappointment or political backlash. To address these challenges, scientists emphasize the need for transparent research, long-term environmental monitoring, and careful communication with the public. Emerging technologies may improve precision and reliability, but they will not eliminate the fundamental variability of weather. The future of cloud seeding will therefore depend on integrating new innovations with realistic expectations and with policies that balance human needs with environmental protection. In conclusion, cloud seeding in the coming decades is likely to be more sophisticated, more widespread, and more closely tied to global efforts to adapt to a changing climate. Through advances in materials, delivery methods, and predictive modeling, the practice may become a valuable part of water management strategies worldwide, but its success will ultimately depend on responsible governance, ethical reflection, and continued scientific evaluation. As we reach the conclusion of this exploration of cloud seeding, it becomes clear that the practice occupies a unique space between science, engineering, policy, and philosophy. At its core, cloud seeding represents the human desire to manage natural forces and to bring some measure of control to the unpredictable rhythms of the atmosphere. It is built on solid scientific principles of condensation and freezing, and it has been tested in dozens of countries across many decades. The goals of rainfall enhancement, snowpack accumulation, and hail suppression are practical responses to very real challenges such as drought, water scarcity, and agricultural risk. Yet for all of its promise, cloud seeding is also surrounded by limits and uncertainties. The atmosphere is an immensely complex system, and the outcomes of seeding operations are difficult to measure with certainty. Rain may follow a seeding attempt, but proving that the intervention caused the rain, rather than natural variability, remains an unresolved challenge. This lack of clear causation means that cloud seeding continues to generate both hope and skepticism in equal measure. On the one hand, communities facing water shortages welcome even the possibility of modest increases in precipitation. On the other hand, critics caution that resources might be better spent on conservation, infrastructure, or alternative technologies. Ethical questions deepen these debates because weather is shared by all, and altering it even slightly raises issues of fairness, consent, and responsibility. Who should decide when and where to seed clouds? How do we balance the needs of one region with the concerns of another? And what obligations do we have to ecosystems that depend on natural precipitation cycles? These questions ensure that cloud seeding will always be more than a technical subject. It is also a social and political one, and any future expansion will require not only scientific validation, but also legal frameworks, international cooperation, and public dialogue. Reflecting on the possibilities, we see a technology that may play a modest but valuable role in adapting to climate change and water stress. Emerging innovations such as drones, nanoparticles, and advanced weather models could make seeding more efficient and environmentally friendly. International partnerships could help ensure that the benefits are shared equitably and that risks are managed responsibly. At the same time, reflecting on the limits reminds us that cloud seeding is not a cure for drought, not a substitute for reducing greenhouse gas emissions, and not a way to gain complete control over the atmosphere. It is a supplemental tool, a way of nudging natural processes rather than mastering them. Its value lies in its modest contributions to larger strategies of resilience and adaptation. In the end, the story of cloud seeding is also the story of human ingenuity and humility. It demonstrates our ability to understand and influence complex natural systems, but also teaches us that nature cannot be commanded outright. Clouds may respond to our interventions, but only when conditions are right, and only within certain bounds. The lesson of cloud seeding is therefore one of balance, of working with the atmosphere rather than against it, and of accepting both the potential and the limits of weather engineering. As societies continue to grapple with water scarcity, climate variability, and the uncertainties of the future, cloud seeding will remain a fascinating example of how humans try to adapt the skies to their needs while still learning to live within the patterns of the natural world.